Yes, I haven't forgot to record so far. Okay, talk more about transmission lines and the effect of open and shorted lines. Um, some comparisons, velocity factor and electrical length and dielectric. So basically for a transmission line, whether it's coaxial or parallel line, um, it has a characteristic impedance, which is a function of the inductance and capacitance distributed along the line. And the way they define characteristic impedance, if you have an infinitely long piece of that transmission line, the impedance you see is called the characteristic impedance. It doesn't matter if it's open or shorted at the other end, if it's infinitely long. And obviously they don't measure it with an infinitely long piece. So they calculate it based on the distributed inductance and capacitances. And there's formulas for doing that to figure out what the actual characteristic impedance will be. Another factor is the velocity of propagation. We call it the velocity factor. And it's a ratio of the speed of light. In other words, how fast the wave would travel if it was in free space versus how fast it travels when it's in the conductor. And because of the dielectric constant around it, that affects the velocity factor. And part of the formula is, besides the ratio of the two velocities, it's 1 over the square root of the permittivity constant, which is a number they come up with based on the dielectric of the materials and the distances. So if you know what K is, you can find out what the velocity factor is. Usually for coax and some of the other, and twin leads, they'll specify the velocity factor. And it varies quite a bit in coaxes, depending on the type of dielectric. Like polyethylene, which is probably the most common, has more loss than and a different dielectric constant, so it will be a lower velocity factor than you would see in a foam-filled or air-filled transmission line.
Is there a particular velocity factor? I mean, it looks like it's a rate
0.95. 0.95.
0.95.
Bare wire.
It's a lot lower than that.
Well, most of your coaxes are going to be lower than that. Probably at best, maybe 0.988, something like that. And they go down, let's see it as low as 0.6, which makes for short lines physically.
Because I have one of those rig expert stick antenna analyzers, and it measures the velocity factor. And you look at it and like, is that good? I don't know. You know.
Well, okay. So you have to put in the link?
I'm putting.
Okay.
This is like an amazing thing.
I'm not sure how it's doing it without knowing the link.
Well, I think that might be part of what it does is measure the electric length. They don't give you the approximate length of your TV.
Right.
So if you had a cable somewhere, you could, but it's got a lot of features on there that I can not figure out.
Yeah, that's called a TDR function, time domain reflectometer, where you send out a pulse and then you measure how long it takes to come back. And that will tell you the electrical link, not the physical link. So you have to really know Yeah. I guess you can do it. But a nano VNA should be able to do that too. I know you can do the TDR. I found out which end of my coax cable was shorted by doing that. Okay, so the velocity factor tells you that uh, the lower it is, the shorter the physical length of the cable is going to be for a given electrical length. And if your calculations say that you need a quarter wavelength electrically, okay, and you're going to go cut your cable, you have to figure out what the physical length is to cut it. So you have to know the velocity factor. So what is the physical length of coaxial cable transmission line? Why is it shorter than its electrical length? Because the only time it would be the same is when the velocity factor was 1. It means same as free space.
Delta, I'm gonna,
Well, delta sounds pretty good. You knew that. You weren't guessing, right?
well, I felt like the others weren't right at all,
Okay.
and I wasn't sure if that was it.
Yeah. You can almost always throw 2 of them out. They're really wacko. Stuff you never heard of or whatever. And this is just more of the same stuff that I already talked about. So it's the ratio of the speed of light in free space to the speed of the wave in the medium. And it's affected by the dielectric materials surrounding the conductor. And between the conductors, in the case of coax or even twin lead, it's like on this ladder line, the dielectric is this plastic material that separates them. So what is the velocity factor of a transmission line?
Talk about the speed of light as part of it, so if I were guessing, I would guess D. I guess I am guessing,
The ratios that can be divided.
yeah.
I guess that's right. Somebody was thinking the other way around. Which of the following has the biggest effect on the velocity factor of a transmission line? Charlie. Some typical values, polyethylene, the solid is down to 0.66. Foam is 0.8. Air insulated or open wire is 0.98. And they usually use a figure of 0.95 for bare wire. And a lot of some of the questions where you have to calculate the length of an element will want you to use that correction factor of 0.95. In fact, one of the formulas that's out there for doing it in feet includes the 0.95 factor in the equation. I think it's the one that's 489, and you divide into that. What is the approximate physical length of an air-insulated parallel conductor transmission line that is electrically 1/2 wavelength long at 14.1 megahertz? So half wavelength at 14, which is 20 meters, right? So that'd be 10 meters. And if it's air insulated parallel, velocity factor was what?
5. Or 28%.
So,
Huh?
Charlie?
I don't remember off the top of my head. And this one, oh, and I did this because if you looked at the study guide, the answer, the explanation he shows in there is when you multiply the 10.64 times 0.98, he comes up with 10.6. That's not right. He come up with 10.4,
No, the 20 meters.
but it's still 10.6 is the right answer because it's closest one.
Where did you get the 20 meters?
14 megahertz divided into 300.
Gotcha.
Remember that formula?
If you
300 divided by the frequency in megahertz gives you the wavelength in meters.
So if you do 300 divided 14.10
Mhm.
divided by 2, it comes up exactly 10.6.
I see.
It's close to the actual formula.
But once you get used to operating on the different bands, you remember what frequency is what band and so forth.
Yeah, that'd be nice.
Yeah. It's like learning Morse code. What takes practice.
Traumatic?
So when we're talking dielectrics, foam versus solid has a much higher velocity factor and lower loss, but it can't tolerate as high a voltage. So you might have a problem running 1500 watts through some RG58 foam core or something like that, because it could arc over. Everything has a compromise. Which of the following is a significant difference between foam dielectric and solid dielectric, assuming all other parameters are the same?
One of the rare.
Yeah.
It's the only one so far today, anyway. Feed line loss. That's part of the thing we took into account when we did the effective radiated power was the feed line loss. So, I mean, that's power that's not getting to the antenna. It's just generating heat in the transmission line or the circulator or whatever it is. In most cases, you're going to be dealing with coaxial cable to connect up to your antenna. You might do something with the parallel line like the G5RV, but still it has a balun that connects it back to coax at a certain point. But there are some cases where you might have a tuner. I have an old one that actually has an output for ladder line, 600 ohm. So you can connect directly to that. And it'll do the match for you. It has much lower loss than coaxial cable. It's more difficult to use. And it's harder because it can flop around in the wind more. Whereas coax, you don't necessarily care if it's next to a ground because of the Faraday shield effect. So it doesn't affect what's in the inside of the coax, just the outside. Where twin lead is affected by what it's close to. So when you used to run the 75 ohm twin lead up to your TV antenna, you had to put standoffs on the house so it didn't get close to the gutters and various things, keep it separated. With coax, you can bury it in the ground if you got direct burial covering. And they're comparing it to RG58, which is fairly high loss cable, but it's easy to use. And in short lengths, it doesn't make any difference. So you use it as patch cables in your shack to connect things up. Actually, most people use RG8X now. It's the same size, but it's more flexible. And it has a little bit lower loss, I think.
That's what you're using earlier, I think, that it's calm mode shows.
Oh, okay.
Yeah. Let me tie it down.
Yeah.
So you need really flex.
Right. You have to have one that allow you to have that smaller bend radius. You won't be doing it with LMR 400. How does parallel conductor transmission line compare to coaxial cable with a plastic dielectric? Which two can you throw away? Yeah. So it's alpha or delta? Okay, matching using coax. I can't say I've ever done this with a 1/8 wavelength piece of coax, but there's certainly no reason why it doesn't work because it would give you an inductive reactance if it's shorted on the end. It would look the opposite if it was open. And depending on the frequency, it may work out that that is enough to do the match to whatever the load is that you're trying to do. I think the important thing to remember is the effect of shorting one end versus having the end open. And you tend, if you think of it as a quarter wave, it's going to be just the opposite. Short's going to give you an open, open's going to give you a short. Eighth of a wave is going to be the inverse, but you're not going to have the full short or open. It's going to be higher or lower than what you're doing. This is just showing it with the stub where it's shorted. And maybe in this case, it was an eighth of an inch, eighth of a wavelength stub, I'm not sure. It was the only one I could find that sort of showed the configuration. What impedance does a 1/8 wavelength transmission line present to a generator when the line is shorted at the far end? It was shorted and it's an eighth of a wavelength long. Instead of being infinite impedance, it's going to be what?
So I think it's C, but I'm trying to wrap my head around.
I had no idea.
Bob,
So it's-
you gave us
Yeah,
a clue there. You said the opposite of infinite. I would say that's zero, but then again, I'm just guessing.
well, because it's only an eighth of a wavelength, okay, if it's shorted on one end, instead of being infinite, it's going to be something less than that. The question is it going to be inductive or capacitive? Because you're going to have a
Got it.
phase. It's something that's easy to see on the Smith chart. We're not there yet. So for now, you just have to remember
Yeah, I just trying because if that was
it. Right.
on your listing there, and he said, hey, make sure you know these two. So.
Right.
uh,
So what impedance does it have? If it's open at the far end,
Yeah,
okay, if we use a quarter wave piece of coax as a match, okay, it gives us a very low impedance when it's open at the opposite end. Essentially, it looks like it's shorted, and just the opposite, it looks like it's a high impedance when it's shorted at the other end. If you do a half wavelength, it's really 2/4. So if you short it at a quarter wave, it's infinite. Another quarter wave is shorter.
Okay, that even freaked me out more.
And if it's open, it's shorted and it's open.
yeah. It's like being in a foreign language class.
What impedance does a quarter wavelength transmission line present to an RF generator when the line is shorted at the far end?
Okay, so the eighth, it was capacitive, when I finally find that, but it switches when you get to,
Well, yeah, at a quarter, it's resistive. It's either high or low. You don't have reactance.
Okay, so you say, would be B,
So let's see, it says we're shorted at one end. It's a quarter wave long. So it's going to be the opposite at the other end. What's the opposite of a short?
right,
A very high impedance.
okay. I need flashcards.
Yeah. Well, that's a concept you need to understand about the wavelength and the way it affects it. Okay, try this one. If it's open at the other end, what is it?
D,
That the same one?
no,
Oh, no, half wavelength. Okay. So a half wavelength shorted at one end is going to be what at the other end? Remember?
B. Should be B,
sure.
Low impedance.
yeah,
They don't call them shorts and opens. They say low impedance, high impedance. And microstrip. This is another thing with dealing with dielectric. And for high frequency, like UHF things, when they're doing circuit board layouts, they'll actually create little transmission lines so they can control the phase shift of signals. And they call it microstrip, where you calculate the width of that conductor and what the dielectric distance is to the ground plane. such that it's like 50 ohms. It looks like a 50 ohm transmission line. They do the same thing with what's called strip line, where it's actually embedded. So you have a ground plane on either side of it. It acts more like a coax as far as a shielding effect, but you still do it such that it has a 50 ohm or whatever, usually 50 ohms. And you also, for the high speed stuff, try to keep the length of them the same, so you don't have a phase shift. So what is microstrip? So. Well, that was an easy one, wasn't it?
Yeah, that one's short circuited, mine.
Yeah, also almost,
Yeah.
I mean, I just slid right through that one. Kind of